Okay, AP Physics. So I am going to go over the FRQ in this video. I am going to try my best not to give you directly all of the answers, since I still want you to be able to use this as a way to work through it, but this should be able to help kind of solve some of the issues that you've been having in terms of what they're asking you for. So I have it set up here where I can see both this and that. So if you see me looking at over here, it's just me reading the question, that kind of stuff. I have my little whiteboard. I'm going to kind of try to go through and show you what they're asking you for that. And again, I'm going to try my best not to answer literally everything for you, but this should help you as a little guide for the FRQ for Unit 6, which is simple harmonic motion. So question 1 says, this question is a long free response question. Show your work for each part. So make sure you are showing as much as you possibly can. Don't just give the easy response. Give what you think is a complete response, right? Yeah, so just try not to overly simplify everything, and you should be fine. In a physics lab, a group of students are provided with a sphere of unknown mass, a roll of string, a ring stand, and measuring devices commonly found in a physics lab. The students must graphically determine the acceleration due to gravity near the Earth's surface by putting the sphere into simple harmonic motion. So what we're going to do is build a pendulum. And when we build our pendulum, the main thing is that we remember that pendulums only go simple harmonic motion under 15 degrees. We didn't really cover why. It has to do with this idea that we talked about earlier, which is that the restoring force has to be equally proportionate and tied to the displacement. So in other words, when we have a spring, I pull back the spring, and how far I pull it back is directly related or directly proportional to the restoring force that I get back. Now with pendulums, because we have this angle as we go up, it actually does change. The further up we go, the more that gravity wants to bring us straight down, right, as opposed to along that curved path. So only within about 15 degrees is our displacement more or less directly proportional to our displacement. So the idea being that sine of our angle is roughly the same thing as our displacement within 15 degrees. And then outside of 15 degrees, sine of that angle is no longer really about our x, and so therefore it's no longer directly proportional or directly tied to how far back we pull back the item. So again, that's why simple harmonic motion of a pendulum only works within about 15 degrees. Okay. So we are going to be building a pendulum, and we know that the period of our pendulum, or at least you should know this by now, or at least be able to identify it, right? At least be able to identify this in a list of equations. But T is equal to 2 pi square root of m over k. Nope, that's for a spring. That's for a spring. Sorry. That's L over G. So excuse me. For a pendulum, that is 2 pi L over G. L being the length of the string, G being the acceleration at the part that we're at. So you can see that we can clearly use this equation to find G. Which is going to be the acceleration, which is what they've asked us to do. So the main thing is just pointing that out and just saying that these things are kind of related to each other. We can see that these two things go along with each other. Yeah, for the most part. Cool. So that's really it. And you will want to probably state that within 15 degrees. I don't know that you need that. Let me check to see if you need that for the full scoring. Let's go all the way back to part A. Nope, all you have to do to get full scoring for part A, according to the AP, is just include that equation. So just make that a statement, hey, this equation tells me that if I know the other things, I can solve for G, right? If I know the period, which I can measure for, and if I know the length of the rope, which I can measure for, then I should be able to find out what G is. So then we get to part B, and part B says, what are you going to measure? What's the symbol for that quantity, and how do we measure for that? So we're going to measure the period, and we just need a clock, right? And the clock is going to tell us that we go up and we come back, and that's how long does it take for us to get back to where we started, right? So the next thing we're going to have to measure is the length of the rope, and for us to measure the length of the rope is going to be a meter stick, something that measures length, like a caliper. We used that in class before, just whatever you might be doing. And the other thing is you might want to include a protractor for measuring angle, because again, if we go beyond 15 degrees, this is no longer simple harmonic motion. So I'm going to again look at the scoring here. I'm going to kind of take a look at that. So yeah, there is something you want to make sure you point out when we're talking about this part A is making sure that you realize, or part B, excuse me, that you realize that we are going to want to measure that because 15 degrees is our cutoff, right? Once again, because outside of 15 degrees, the sine of our angle is no longer essentially what our displacement is. So that's the big reason. Again, you can look up plenty of videos on that. Simple harmonic motion involving pendulums, it'll explain that. Cool. So again, that's what do we need to measure. And part B says, can you design that experiment? So that's what we're going to do. We're going to measure to make sure we're within 15 degrees. We're going to take this thing and we're going to let it go, right? And when we let it go, we're going to make sure that we measure it, the time. You need to make sure your responses are a lot more detailed than what I'm giving you. Again, this is an overview. So when you put that in there, design the full experiment. Say exactly what you need to do in exactly those terms. Try to be as specific as possible. You don't need to go ahead and like do what's my problem, what's my hypothesis, what's my question, all that kind of stuff. You don't really need to do that per se. This is really looking more for listing the type of equipment that you're going to need. You're going to need to list on kind of just your procedure in general, making sure that you're listing the procedures for measuring everything that we possibly need to find here, and that we're looking for kind of the back and forth. So we're really looking more for a procedure and saying that you're going to go get these pieces of equipment and how are you going to set them up. We're not really looking for any sort of conclusion, results, data, anything like that. And we really don't care too much about the hypothesis unless specifically stated, which I doubt they will. Okay. So unless they specifically state, hey, I want you to use, give us a hypothesis and kind of go from there, then don't worry about it. Just give the procedure. And again, focus less on the setup and the setup being like your visual setup. How does my procedure look? And focus a lot more on what are all the pieces that need to be taken care of in order to make sure that I get exactly the result that I need. Okay. Cool. So that's part B. And this we're going to design an experiment to measure that, and we'll find G, ideally. Cool. So part C. Part C says the students must graph the data that they have collected so they can determine the acceleration of gravity near the Earth's surface. Indicate below which quantities could be graphed on the horizontal axis or the vertical axis to determine the acceleration due to gravity near the Earth's surfaces by using a best fit line. You may use the remaining columns in the table above to record any quantities that are not already in the table. But you don't need to do that. All we have to do is take a look at the equation that we've been given and say, how could we graph this equation to let me find G by using that graph? Okay. So we're going to show you that. We'll do that together. So essentially, I have a little graph section here. Let me know if you can or can't see it. We're going to use the pieces that we have. This is clearly almost like y equals something x, and so we're going to use t as my y. Pretty straightforward. We're going to use t as my y, and we're going to find something over here that changes that I can use as my x. Well, the only thing that would change on this left-hand side would be L, since G shouldn't change, right, if we're at the same location, and 2 pi is a literal number. It's not a variable, so it shouldn't change. So we're going to come up with some graph, or we can graph those things against each other. And here, give me 1 second, sorry. Oh, I had a stupid drag in here to wipe this off, and somebody took it. That's fine. Use my shirt. Cool. So if we have t is equal to 2 pi square root of L over G, there's a couple different things we can do here. We can go ahead and say that t is equal to 2 pi over square root of G, and then we have square root of L, my length. And what we can say here is that t is going to be my y, and that square root of L is going to be my x. And so therefore, this would give me a slope of a graph where this term is my slope. You can even make that a little different if you want. I mean, make it simpler if you really want to. You can say, well, let's measure t squared is equal to 2 pi, excuse me, that's going to be 4 pi squared. We're just going to square both sides. 4 pi squared over G times L. But now you just have L as your x, and t squared will be your y, and you'll graph those two things against each other. And if we were to graph those two things against each other, then it'll give us a graph where the slope is that term. So let's say we do that. We have t squared, and we have L down here. If we do that, that should give us whatever is that first coefficient as our slope. Right? And so therefore, we should be able to find G using that. If you still have problems with that and you can't figure out exactly what I mean by that, if you watch the video, try to make sure you watch this a couple times before you go through and ask it, because you should try to think your way through it. But essentially what I'm saying is, think about if this was y and x. Well, what would that make my slope? Hopefully that helps you out a little bit. And you can see that G should be a component of that slope. And because of that, we should be able to go back and find what G is. Okay? All right, and again, make sure you write all of this out in full, complete sentences and terms if you want to get credit for the FRQ. Because again, I'm doing it for you right now, so just make sure that you don't let me do all of it for you. You are trying to build these skills. Okay, so that was C1. C1 says find an equation where you can find a slope that G is a part of. And that way you can use that to graph these two things and go back and find what G is. And again, if we look here, 4 pi squared is an actual number. So that's going to stay the same the whole time. So the thing that's going to change will be G. So we can always find out what is our slope, set this equal to it, and that will give us, again, a way for us to find G. Right. Okay. So the next part, again, says, hey, what if mass was your slope? What they literally mean for you to do here is for you to be able to take m and set it equal to that coefficient term that was your slope from the previous problem, right? We came up with an equation where we have a coefficient term that represents my slope, right? My t term, whatever it ends up being, t squared or t, is my y term. My x term is going to be L, whatever way we end up representing it. And so everything else that's there, since it's not added, it's not a translation, it'll be a coefficient term, will be my slope, right? Take that whole term and you set it equal to your mass. And that's what they're essentially saying. And then what they're saying is there a way for you to use that and find G if you knew that? So find some way about going about doing that. So just make sure you can see that. And again, if you have more questions, we're going to be meeting on Wednesday. Send me all the questions that you have. We meet Wednesday from 10:30 to 11:30, and we'll start running through this stuff. Yes, you have other assignments this week on torque and rotational motion, and I do want you to start running through those. But remember, our test is FRQ based, and so many of you guys have not really gone through and started doing it yet that I want to make myself available to go through something, right? We don't want to be putting ourselves out in a bad way. So just let me know. Cool. So that is part C2. And then part D. Part D says we have this pendulum and it's swinging back and forth, and we have these 3 spots. And when it gets all the way up to this spot, it's X. And when it gets all the way up to this spot, it's going to be Z. And it's probably reversed from your standpoint, but that doesn't really matter. So again, we get all the way up to Z. And then we're going to cut this line. Well, remember at Z, we have no velocity. We have all gravitational, and in this case, it's all gravitational energy. In fact, that's all we're going. We're going back and forth between gravitational energy and kinetic energy, right? Our rope doesn't have any spring energy in it. It's not storing any chemical energy. So we're just going back and forth between these two things, right? We used work to give it this gravitational potential energy, and we let go of it, and it became kinetic, and then it became gravitational. So at either end, at either maximum point, we don't have any kinetic energy, so therefore we're not moving. So what's going to happen when we cut this rope? Well, if it's not moving, it's not going to fly off, and that's the main point here. Is you can use that idea to solve for the rest of the question. It's pretty straightforward, to be honest with you. After that point, but just make sure you realize at our maximum points we don't have any velocity. And why don't we have any velocity? Well, that's the definition of it being at our maximum at this point. Is that we have all one type of energy, and that type of energy is not kinetic, right? For springs, it's spring energy, right? At our maximum, we're not moving, but we have spring energy. We go back and forth between these 2 spots. Right? Okay. Cool. So let's look at question 2. Question 2 is actually shorter and I think a little bit easier. So question 2, the main thing for us to recognize is they give us this graph. It says, here is this graph of this spring energy, and it looks like this, right? And it goes from being positive down to 0 and back up to being positive. Remember, we can't have negative spring energy. 1/2 kx squared, k is always positive, and if x is ever negative, we square it, so it doesn't matter. So we can only ever have positive spring energy. The main thing to recognize here is that that's not true of spring force, right? Because when we take a look at spring force, we'll notice that our spring force will actually always have the opposite sign of our displacement, because spring force is negative kx. So if I were to stretch a spring back, like, let's say 5 meters, well, then my force is going to be negative, the opposite direction. It's negative. But if I were to stretch that thing back negative 5 meters or compress it negative 5 meters, then you can see that that again will give us a positive number. So that's the main thing to recognize for most of this. It's actually relatively straightforward and easy once you take a look at it that way, is to recognize that we do have these 2 different relationships. One is, well, how can I find out what K is? Well, that's pretty easy. We can find out what K is by using our spring energy. We have a graph. The graph literally tells me what my spring energy is, right? So all I have to do is take from that graph two pieces, two things that I literally know that they gave me. They literally give me what's the spring energy on that graph. If you look on there, it's the left-hand side. And they literally give me what is the displacement, right? What's my horizontal position? So they give me everything I need to solve for K, which is awesome because I'm going to need that eventually, right? So that's the first part. The second thing is to recognize that they're going to ask us to solve for this force and graph this force. And we can use the graph above to go back and solve for these things. We can solve for K, which we can do. It would be pretty easy. And we can also go back and recognize that no matter what my input is, in terms of my displacement, my force is always going to be the opposite of that. So if you look at this graph, it doesn't give me any units, right? And so if I'm being confusing here, make sure you pull up the graph, and I'm going to run through the whole thing again here. So question 2 gives me this graph, spring energy. It tells me what my displacement is, how far away am I from the center, and then it gives me what is my spring energy at that point. I can use that to find K. It's all the pieces I need, right? And that'll come up. We'll need to find that here in a second. The next thing is, it also allows me to at least know relatively what my spring forces are. At my maximum amplitude, my spring force is going to be at its greatest. At equilibrium, when I have no spring energy, I also have no spring force. So spring force will be at 0. And then when I go back towards my maximum amplitude in the other direction, then I'm also going to start incurring this spring force. The main thing to recognize is if I go to a negative position, my spring force is positive because the negative kx, right? I have this negative kx. So if I go to a negative position, spring force is positive. If I go to a positive position, spring force is negative. That's it. That's all you need to solve for that first part. Part B, calculate the period of the oscillating spring system. Well, that is where we need that K that I told you we could solve for. T is equal to 2 pi square root m over K. Cool. So they give us the mass, right? In the problem, they literally tell us what the mass is. So that's not anything we have to solve for. And then they've asked us, can we solve for the period? Well, the only thing we need is K. Well, remember, I told you we can solve for K. We can do that. They give us in that graph, what's the spring energy? They give us in that graph, what is my displacement? And so therefore, the only unknown there will be K. So you can solve for that. Now, you might be making an estimation that's relatively close, but you'll be fine, right? That's what they're looking for, is for you to be able to do that. So for part B, that's all we have to do. Solve for that K, plug it into that equation. They give me the mass. I'll find for the period. Remember, the period represents how many seconds does it take for this object to repeat a cycle. So I go down and I come back up for a pendulum, or for a spring, I actually, if I pull it all the way back, I have to go through and then come all the way back for that to be one period. All right, this is a heads up. Cool. Part C says, can you represent the kinetic energy? Well, when we pull this thing all the way back, all of that energy is going to be spring energy. So whatever my number is for my maximum spring energy is going to be my number for my maximum kinetic energy. And my kinetic energy is going to go from having none up to its maximum, back down to having none, right? So in other words, I'm going to pull this spring back. I have no kinetic energy. I let it go. At its equilibrium point, it's all kinetic energy, the same amount of energy I had for my spring. And then I go all the way back to the other, and I'm back down to 0 because I'm not moving anymore, right? I stop, and then I turn around. So that's what it's going to look like for part C. And you can use the numbers from there and make sure you do that properly. And really, that's it for the 2 questions. Obviously, if you still have more questions, I just recorded almost 20 minutes worth of video. If I'm going too fast, play it slower. You have the option to do that. If I'm talking too quickly, or if I'm throwing a lot at you, or the things that I'm saying are a little confusing, try to rewatch it, because I think that I reiterate a lot of the things. So just make sure you can see that. And if there's still something that doesn't make sense, or you don't understand how we were supposed to get that, just ask me. Again, we'll have a meeting on Wednesday. You just let me know. This is for your viewing pleasure for FRQ, again, for Unit 6. Please make sure you're finishing up all of that work and moving on to this week, which is torque and rotational mechanics. This week, what we're learning about has more to do with understanding things like alpha and omega. And that is pretty straightforward. We're looking this week at talking about a thing called omega, and we're looking at a thing called alpha, and we're looking at theta. Now, theta in radians represents my displacement. It's basically the same thing as talking about displacement, or x, that we talked about in the very first chapter, right? Now, alpha is just the same thing as saying what's my angular acceleration. So it's basically the same thing as saying a. And omega is basically saying the same thing as what's my angular velocity. You may be saying, well, why do we have different symbols? Because I'm spinning. Well, the main thing is that these things all put this in terms of the spin. How many spins do I complete? Not really the distance, but how many spins do I complete, really? That's kind of what they're talking about there. for the most part. So we're kind of introducing that idea before we move on to torque. That does mean that when you go through the multiple choice questions this week, that there will be some things that you don't recognize, don't understand. What I would prefer for you to do is, rather than panic or kind of like, I can't finish it, work your way through it, and whenever you run into a concept you can't understand, write it down as a question, and then we'll cover those as we go forward, right? So we're going to watch the first half of these torque questions this week, and then we'll watch the second half of the torque questions next week and kind of work our way through that as we go along. We still have literally a month before our test, so not worried about it. I think we should spend 3 weeks on torque, get a good general idea on how do we solve for things, and get a good general idea on what are they asking me for, what are the things I need to be looking for, what do all these symbols represent, which is really the big thing. And then we'll spend another week or two on going back to kinematics and forces and doing general stuff like that for the most part. So yeah, I would be just kind of looking out for that stuff, and you just let me know what you need or don't need. Hopefully this helped you out. Let me know. Please comment. Please send me an email. Let me know, do you want me to answer questions like this or not? Immediately, feel free to do it immediately in the comments. Hey, this helped me out. Hey, this didn't help me out. Just let me know.